All right, welcome back, everyone. We'll give it like another minute or two, see if anyone else joins in, and we'll get started. All right, welcome back. Let's go ahead and get started. The first thing I want to point out, we had some technical difficulties last week. I was able to resolve that. I posted a Zoom recording link, so essentially I just recorded an entire lecture, walked your way through. I will point towards the slides I used. What I determined was video wasn't the best way to go, and it's better just to do a bunch of screenshots. And let's see here, pop this open real quick. For those of you that might not have had the opportunity to watch that yet, but essentially what I did, I'll scroll through this real quick. So the first night, September 24th, we talked about hand calculations, PSpice simulations. So specifically, this is a PSpice simulations, right? We talked about how to set up PSpice and do whatnot. And recorded lecture, I talked about Protoboard basics. I'll sum it up real quick. If you've never looked at one of these before, I just want to point out like these top and bottom rails here, your power supplies, they're connected all the way across. Then the ones in the middle is your proto area. This is the area discontinuity down the middle. And the columns are connected connectivity wise. So for example, you got like your 741 here, it's plugged into one of the holes. And each one of these holes in the column right here is connected to that pin. So just give you a little background. I talked about the 741. It's an 8-pin dip, dual inline package. I got a nice pinout diagram here so you can see how everything maps to the op amp itself. NC, I call that out. That's just a no connect pin. It's not used. It's just for mechanical stability. You have two offset null pins, 1 and 5, which aren't used in this lab or any subsequent labs. But if you're curious what they're for tuning and offset voltage. And here, down here on the right, for illustrative purposes only, and is an example circuit about how you go about tuning that. Your power supply pins are pins 4 and 7. So this lab that you're working on right now is a dual supply lab, right? So you're going to be using positive 5 volts on pin 7, negative 5 volts on pin 4. Next week, you'll be starting your single supply op amp lab. So the only difference will be you'll still have positive 5 volts on pin 7, but pin 4 will be ground. So it'll be at 0 volts here. I've also included a link for the data sheet. That's helpful if you want to look at things in terms of what the open loop gain might be, what the maximum frequency or max operating conditions. So just a recap for this lab, you're building up 2 circuits, right? You're doing a non-inverting amplifier and an inverting amplifier. I built this up on a couple different ways for you here. One on the Protoboard to kind of show you how I'd wire it up. Then I took a snapshot on my board. It's not the easiest to read. These are pretty small resistors that they provided you with, but you kind of get a general idea how I'm trying to minimize the amount of wires I use. One thing I will say is this, like for example, like these power supply ones, my red and blue here, I just connected the power supply directly to the red wire and blue wire. So I didn't plug it into the board. You can do it either way though. It's up to you. Then it just shows you the representative of the schematic, how to connect everything up. I didn't take a picture for the inverting op amp configuration, but I still kept this picture in here for you so you can kind of map it and see the difference. The key between the two is RA is grounded. So this is actually your ground connection right here. And your input is provided directly into pin 3, the non-inverting input. Then the only thing you change on this configuration is you ground the non-inverting input. So that's this yellowish orange wire coming up here. So that's grounded. Then now your input is applied directly to RA, right? So this is where your function generator hooks up. I talked about the analog discovery kit a little bit. I just showed how I went through and I labeled all the wires that were provided, with the kit. I essentially disregarded everything from right of the triggers over for the digital I/O signals. I just zip tied those behind it, kind of bundled them up on mine. Like, it's up to you. I just do it for house, keeping purposes. Makes it a little easier to keep track of what wires you're using. Let's see here. Analog discovery components, I talked about that. So here's all the parts you're provided with. Hopefully by now everyone received the 741 op amps that I mailed to you. I also included some 10 microfarad capacitors that we'll use in a later lab. So don't worry about the ICs for this lab. You have the 741. What you are going to need though is the resistors, right? So based on the lab write-up in the beginning, they kind of give you a spec and they're like, hey, go pick out an RA and an RB within a given tolerance range that provides a specified gain, right? Unfortunately, unless you went out and bought one on your own, and that was something I kind of talked about, like if you want to go to Harbor Freight and get like a really cheap multimeter for like 10 bucks, go ahead and do it. It makes it a little easier to do impedance measurements. The Analog Discovery 2, from what I've seen, it doesn't have that capability. I could be proven wrong. I haven't spent enough time playing around with it yet, but it doesn't have like a true multimeter capability built into it where you can do voltage, current, impedance measurements. So here's what you have, what they provide you with. They tell you how many resistors they're given to you, what their nominal value is, then they give you the color code for the 3 resistance bands, right? Then you might be asking, well, what are these bands? What are you talking about? Well, if you pick up the physical resistor and you look at it, yours have a 4-band code. The colors map to a number, and really you just want to disregard the 4th one. That's just the tolerance. I'm pretty positive the majority of them in here are gold, so they're plus or minus 5% of whatever the specified value is. So really what you want to do is pick them up, kind of match them up with the color code, and that's how you pick your values. I'll be honest, like the bands are pretty small. If you don't have like a magnifying glass, I just used my smartphone and zoomed in on the camera and took pictures of them. Made it a little bit easier. All right, next thing. How do you connect the Analog Discovery 2 to the circuit? So I kind of drew that out for you here. So you're going to be using, you got to connect your ground. And again, you don't have to connect it right here to the rail. You can just connect it directly to this point right here. Then you got your positive power supply, same thing. Negative power supply here. Those were, what else? Then you got your function generator, which is W1, feeding in right here. And keep in mind, this is the non-inverting configuration, right? I'm just showing it for one of the circuits. Then you're going to have your oscope, and you're going to do channel 1 and channel 2. So probably the preferred initial startup is to look at your input signal and your output signal. For some reason, if it's not working, then you're going to want to do some troubleshooting. So here's some tips on troubleshooting that I went into. Well, why do you do it? Well, obviously things don't always work out as planned when you connect it together. You're going to have to use the tools at your disposal to diagnose the issue. I recommend the divide and conquer approach. So typically this begins with, hey, my output is bad, right? So next thing I would recommend is, well, check the input. Is the function generator turned on? Is the oscope running? Check your supplies. Is your circuit biased up? Does it have power to it? If all those look good, the last thing you're going to want to do is check the bias point at the intermediate nodes. You can use the oscope with the voltage. There's a measurement capability on it. I'll go into that in a second. Or you can just, use your, say, leave channel 2 on, right? Because that's what you're looking for. See if you're getting a good out. And channel 1 is good because that's your input signal. So pull your scope channel 1 off and start probing around at these intermediate nodes, checking your power and whatnot, and make sure everything's connected right. 9 out of 10 times it's going to be one of, well, two things. There's three possible issues. The first two will be your test equipment is not set up properly. So maybe your power supply isn't turned on, your function generator is not turned on, or your oscope's not turned on. The second thing would be you have a connectivity issue. So maybe one of your wires wasn't pushed all the way down on the breadboard. Maybe you had the op amp, flipped around, or maybe you had the resistors inverted or something like that, or maybe you had the power supplies configured wrong. The very last thing is you have a bad op amp. So that's why I mailed 3 of them to you. So that's the last thing you should check. The last thing I talked about in the video is lab report. Okay, so tonight's going to be the last night of this lab. The report is not due until next Thursday at 6 p.m. I'm asking that everyone submits it via Moodle individually, and here's what I want from you. I want to see your hand calculations for the steps up front. You can take a screenshot of them, you can scan them, take a picture, just embed it in your Word document. I want to see a screenshot of your PSpice schematic just to see that you built it up, a screenshot of your simulation plots, and a screenshot of measured outputs in the lab steps. I want you to answer conclusion items 1 through 3. Then up top, what I skipped over, and intentionally, because I'm going to pull up the lab right now, is I want you to complete steps 1 through 16. So let me jump over to the lab real quick. So we're doing lab 3. And I say 1 through 16 because there's actually more than that. 1 through 16 will get you through the inverting and non-inverting configuration, right? Beyond 16 is when they ask you to do a couple other things, like if you want to build a differential amplifier like this, and there's a couple of gain stages, different ways of using a differential input. These aren't required. This is a very lengthy lab, so I cut those out. But by all means, if that's something that you want to continue on your own and do, you're encouraged to do so. I believe I called out steps. Yes, steps 1 through 3. So just answer these conclusion items directly. They're pretty straightforward. Let's see if there's anything else. I think that covers it for that part. So I also have the data sheet posted here, the slide deck. Here's a recording where I actually went through, talked about everything last week on my own on how to configure everything. And I did an example with waveforms. I will jump over to waveforms right now and walk you through everything. Actually, how about I do this? I'm going to close this out and just start from scratch, right? It's always better that way. So let's go to Waveforms app. I'm going to launch it. So I've got my Analog Discovery 2 hooked up to my circuit right now. It's plugged into my USB. So the first thing I'm going to do is select what I need to use within my workspace, right? So I'm going to select supplies. I'm going to select WaveGen, and I'm going to select scope. So you can see up here, I have 3 tabs now, right? I got supplies. Let's start there. I'm going to come in here. The maximum voltage is positive and negative 5 volts. So we're going to be using 5 volts on the positive supply. I want both of them to initially track. So if I want to come in here and change things, I want them to track. But if you need to experiment at some point and you need asymmetrical rails, so that would be the positive or negative supply being of different values, you just unclick the tracking. So I'm going to leave tracking on. I'm going to hit master enable on, and that turns my power supplies on. So I now have positive and negative 5 volts applied to my circuit. I'm going to go to wave gen, and you can see here, you can come in and do DC if you want to do that, and you just select DC values to step through. So you could do -5 to positive 5 volts. I'm going to select, there's a bunch of waveforms in here, right? I'm just going to go with sine wave. That's what we're going to use for this one. Let's see here. They got a ramp up one and a ramp down. So if you want to do like a DC sweep, you could use those. So let's start with sine wave. I'm just going to do 1 kilohertz at a 1 volt peak. Let's see, what's the gain of my circuit? That'd probably be a good thing to tell you right now. The gain of my circuit, I'll just say it's approximately 3. It's actually like 3.1. But okay, so we got a 1 volt peak, 1 kilohertz signal. So it tells you the frequency, the period, the symmetry. I'm not doing a DC offset. I'm not doing a phase change on the circuit. And I'm going to go ahead, come up over here, and I'm going to hit run. So now it's running. We got the green box on, right? We got signal being applied. I'm going to come over here to my oscope, and you can see I have channel 1, channel 2 selected. They each have a range of 500 millivolts per division. So that's the y-axis, right? Time is your x-axis. So coming across time, it's 1 millisecond per division. So a good thing is, before you even plot something, you should have a little thought experiment at this point, which is, what do I anticipate here? So let's go back to our wave gen. I have a 1 kilohertz signal that has a 1 millisecond period with a 1 volt peak, okay? I told you the gain of my circuit is approximately 3. So I expect the output to look like the input, both track each other in terms of phase because it's a non-inverting amplifier, and I expect the output to be 3 times larger than the input. Now, I have 1 millisecond per division, so I expect to see multiple cycles of the signal coming across the screen, right? Okay, so let's see what happens. We're going to come up here, we're going to hit run, and there you go. There's a waveform. So you got channel 1 and channel 2 being plotted right now for my circuit. Well, initially you might look at this as if you're your first time using this equipment and think to yourself, man, my circuit doesn't look right. Here's my input signal. I got my 1 volt peak, right? So 2 volts peak to peak. But my output's being clipped to like 2.5 volts. Man, this looks horrible. It's not doing what it's supposed to be doing. What's wrong with my circuit? Well, that's when you have to be more intelligent than the tool, right? You got to come in here and be like, well, maybe it's not being clipped. Maybe my scale is wrong for my signal. So let's do 1 volt. Voila, there you go. So now we have a really nice sine wave for both the input and the output. They're in phase with each other, which is what we expect for a non-inverting configuration. Then the next thing we might be thinking to ourselves is like, oh, what's the gain of my circuit? Well, you can use the access here and kind of, do a hand estimate. Just be like, let's see here. Let's keep in mind the first one's 500 millivolts per division. So this is 1 volt for the yellow one, right? Even though it's going up to 2, because it's 500 millivolts per division. If that's tough to look out, we could also come here and just change it to 1 to make it look a little easier. So now you got your 1. Then the other one, our output is at 1 volt per division. So now it's coming up a little over 3 volts. So yeah, we got a gain of a little more than 3, right? Well, what if we want something a little bit more accurate? Well, we can come up here and we can click on measurements. You come over here, click add. We're going to do a define measurement, channel 1, vertical. You can click on the caret there. Let's do peak to peak. Hit add. Let's do average, add, and I'll leave it at that. We'll come to channel 2, do peak to peak, add, and we'll do average, add, and we'll close that out. And now you can see all the values right here, right? So channel 1, which is our input, has a peak to peak of 2 volts. Channel 2, which is our output, has a peak to peak of 6.3. I told you the gain of my circuit was 3.1. So that's pretty close, right? 6.3 divided by 2 is like 3.15. So that's actually one of your item questions, right? Why is it different than the hand calculated? Well, think of tolerances, right? Those resistors don't perfectly match. So unless I went in and I measured them, I don't and know the exact value of them. If I'm just working off of the nominal value that's presented on our kit, there's going to be some differences there. The other thing you might be asking yourselves is, why do these numbers keep jumping around? Okay, this is running in real time. So it's collecting a little over 8,000 samples at 800 kilohertz. So what does that 800 kilohertz tell you? That's the time step. Kind of recall back to the transient simulation, like how big of a step the circuit takes. This is how big of a step it's taken. So it's taking a bunch of samples all the way along these waveforms, and that's how it plots this for you in this virtual environment. Well, what if you don't want it to jump around like that? Well, there's two things you can do. You can come up here and hit stop, and it'll freeze the waveform for you. You could also do a single run like that, and it'll just do one screen capture for you. So that's an alternative way to go about doing it. There's multiple different options in here in terms of putting cursors in and adding notes to it. I'll leave that to you if you want to play around with it. The one last thing I was kind of curious about, we'll take a quick look at. Defined. I wonder if we could do a custom. All right, yeah, I'm not going to play around with this. I was just kind of curious if we could do a defined gain measurement of like C2 divided by C1. All right, so that captures that. So part of the reason I threw the average measurement in here is because if you needed to use your channel 2 oscope probe to probe around your circuit and get DC measurements, that would give that to you. So like right now, the average, as we'd expect for a sine wave, is right at 0 volts, right? Which is right about what we're seeing. They're both about less than a millivolt. If you're asking why they're jumping around, two reasons. There's noise in the measurement equipment, and you're basing that measurement off of these samples. And if these samples aren't perfectly symmetric about a given period, it's not gonna average out to 0, right? So just to show you that the average tracks, I'm going to come back to the wave gen, and I'm going to put a 0.5 volt DC offset in, and we'll come back to scope. And what do we see here? So we see that the average for channel 1 now, we still have a 2 volt peak to peak signal. It has a 0.5 volt offset. And now our gain isn't 6. Why is that? Well, hopefully you notice this is clipping up here, right? This is a form of distortion. This is not an ideal trait of an amplifier. If this is like an audio amplifier for like your car speaker, the noise coming out of it would sound horrible right now. So we look at the average and we see, we got to keep in mind, right? Gain in this circuit is applied to both DC and AC. So what happened? Well, our DC average point, so the point of which this output oscillates about, is about 1.5 volts right now. So 1.5 volts is like our center point for this sine wave, right? Well, we have a gain of 3, so we expect it to be 1.5 plus another 3 volts higher, so that's 4.5. So that's why you're seeing this clipping here. Now you might be asking yourself, well, why is it clipping below 5 volts? Let me come back here. I want to show you something real quick. And again, this is where maybe I got to pull the scope back up here. There we go. Scope, wave gen. Okay. I'm actually going to take this back to 0 to illustrate this point. I'm going to put this in at 2. And we'll go back to the scope. And the reason I'm doing this, I just want to show the clipping on both sides. So you'll notice this clipping right here is occurring a little over 4 volts, right? Like 4.3 volts. And we could use the measurement tools to get the actual value. Then this one is clipping at like negative 3.6, 3.7. So the first thing to notice is Yeah, we had distortion. It's clipping on both. Then the other thing is clipping is not symmetrical, right? So, and what I mean by symmetrical is that the clipping on the positive peak doesn't stop at the same point as the clipping on the negative peak. That's just a characteristic of this amplifier. And this would scale. Like if you put positive and negative 10-volt supplies, the clipping would occur at a higher level, but the delta between here and here would be still smaller than the delta between here and here. So clipping is one thing. Let's see here. Let me go back to wave gen. I'm going to take this back to 1. And another thing I wanted to show you is what happens if you make the frequency too big, right? So now we're doing 200 kilohertz with a period of 5 microseconds. And you come back here. Actually, did I turn that on? Run it. Got to make sure it's running. So that was my first check, right? I didn't see the signal I wanted. Okay, now I come back here and I'm like, all right, I'm getting something out, but it just looks nasty. What is this, right? I'm just seeing like a big yellow bar across my screen. Well, what was our period? It was like on the order of microseconds, and we have a millisecond per division. So we're having like thousands of oscillations per period. So we need to come in here and dial this back, right? So let's come in here. I'm going to take it down to like 5 microseconds. There we go. So now we're seeing several periods. The input still looks great, 2 volts peak to peak, right? But the output looks horrible. What's happening here? This looks nothing like a sine wave. It looks like a triangle wave, right? This is another form of distortion that I just wanted to show to you. This form here has to do with a limitation on, hopefully it's something you've been learning about in class and lecture. It's called gain bandwidth product. So for a given amplifier and a finite feedback network, you'll have a finite gain up to a certain frequency. Once you exceed that frequency, the gain of the amplifier drops off. So that's why the output is actually attenuated compared to the input, right? The other thing that you're seeing here, this is different, keep in mind, there's two different things, two different distortion aspects happening here, is that you're seeing some slew rate limitation here. So what do I mean by slew rate? Well, much like your supplies, which have a rail, a positive 5 volt and a negative 5 volt, your op amp, if you looked at the data sheet, it has a current rail as well. So what do I mean by current rail? Current rail is it can only source and sink so much current on the output pin, pin 7 of your op amp that's driving that resistive load. So you're trying to get the output to switch really fast and produce this really large gains circuit. In order to do that, you got to be like driving a lot of current or pulling a lot of current from that feedback network to make it happen. The op amp is not capable of providing that from what we can see here. So that's why you're seeing a linear rise. It's providing its limit, and when you hit the limit of something, it's just a constant rise up, then a constant rise down. Now, that's what gives you this triangle wave here. All right, I think that pretty much concludes it for the waveform part of it right now. Let me jump back to the op amp lab real quick. I just want to talk a couple of discussion points on what you're going to be doing in the laboratory experiment if you haven't started already. So step 9, first of all the lab steps throughout here, you're going to be using a positive and negative 5 volt supply. This is originally, these labs are written if you're doing this lab with test equipment in the lab. So the first step, you're going to be calculating the offset of your circuit, right? So how are you going to do that? So they're telling you to construct the circuit of figure 1. So that's this one right here. And what they want you to do is to measure the offset voltage of the output. Now what's offset? That's when there's an imbalance between your differential inputs, right? So if you have a positive 5 volt and a negative 5 volt supply, and you have 0 volts on the input, right, which is right in the middle of the two, you'd expect to have 0 volts on VN1 right here, and for the output voltage to be the appropriate amount to give you 0 volts here, right? Well, what output voltage will give you 0? Well, if you have ground here, which is 0, and you want 0 here, that means there's 0 current through RA. Therefore, V out also has to be 0, right? Well, so what you're going to do on that first step, on step 9, instead of applying the function generator, well, you can do it one of two ways. You can either ground this pin, or you can just set your function generator to 0 volts DC with no sine wave, right? Then you're going to use the DC measurement that I just showed you, or the average measurement for your oscope probe on the output. And what you expect to see here is 0 volts. You're not going to see that. You're going to see several millivolts, maybe even tens of millivolts on the output when the input's grounded. So when it asks you to calculate the offset voltage, you have to keep in mind this is a gain circuit. So the offset voltage is what's referred to the input. Like, what would you have to apply on this pin here in order to get the V out to be 0? So keep in mind, whatever V out is, it's gained up by RB and RA. So you have to divide V out down by the gain of your circuit to get the true offset voltage. So that's step 9, just to add some clarity to that. Let's see, what other steps do they have you do? So step 10, you're going to do a DC source varied over a range. You can do -5 to +5 volts. And there's a reason they selected 6 here, is because below 6, -6, and above +6, you're going to have a lot of funky behavior because of gain limitations and everything else. I'd recommend, since we're cutting the supplies in half, cut this in half. So do plus to minus 3. Then just go ahead and collect your data points here. Perform that step. Step 11. So instead of doing a DC source, now you're going to do what I did, which is you're going to have your function generator hooked up. And you're going to do a 1 volt peak to peak, 1 kilohertz triangle wave with 0 volts DC offset. You're going to plot all the waveforms. Now keep in mind, you can only do 2 at a time. I acknowledge that because you have two oscope probes. So what I'd recommend is when I ask for a plot from you, just pick one of them. Like, you know, I'd recommend look at the output and look at the input. Take a screenshot of that, calculate your gain from it. Let's see here, step 12. Let's see, I can already tell you right now that the oscope is set to DC coupling. So what's the difference between DC coupling and AC coupling on your oscope? DC coupling captures what we saw, both the DC component and the AC component. Remember, it's like a gain of both. What if there's like a DC shift throughout your circuit and you want both sine waves to overlap each other? Then you could set it to AC coupling and you get rid of that DC offset of the signal, okay? So what they're gonna do here is kind of what I displayed to you before. You're just gonna keep increasing the signal amplitude until you get clipping at the output. Then they're gonna have you kind of tweak it and maximize, you know, to where you get the maximum input and get the gain out of the circuit. Step 13, you're going to switch gears. You're going to go to figure 2. You're going to build the inverting amplifier configuration. So let's see here. Step 14, this is a little tricky because you don't have a multimeter. They're going to ask you to measure the small signal input resistance of your circuit. So let's go up there and talk about that really quick since you don't have all the tools that you normally have in the lab. So they're asking you, what's RN2 right here, right? So how can you measure that? Well, let's see here. So you know RA, right? Just use the nominal value from what you selected. And you know the voltage going across this, right? Yeah, I guess the tricky part is normally I'd have you measure the current going through the circuit. Let's see. You could do it with two oscope probes and just do a difference between them. That'd be one way. That'll definitely give you the current, right? So I think that's the key thing I'm trying to emphasize here for you. And the trick on this measurement is you got to make sure that your circuit is operating within the linear range. So if you're getting clipping or if it's biased wrong, fundamentally, what's an op amp trying to do? It's trying to get both of its input terminals to be equal to each other, right, through this feedback network. So by that virtue, since the non-inverting terminal here is ground, the negative terminal is a virtual ground if the op amp is working right? So if this is a virtual ground right here, and you're applying a signal here, and you see 0 here with one oscope probe, and you see the signal here with the other oscope probe, you know that all the voltage is being applied across this impedance, and the input of your circuit then is Rn2, which is Ra. So you can play around with it. You're kind of hamstrung a little bit on that one just by virtue of the lack of tools that you have at your disposal for step 13. What else here? Don't worry about step 14. I would just say you can skip that. Step 15. Okay, that was the last thing I just did for you, which was change it to a sine wave and just keep pumping up the frequency. So play around with both, right? Like again, kind of tinker is what I'm recommending here, which is have a small amplitude signal and increase the frequency really high, then have a large amplitude signal and increase the frequency real high, and kind of see what happens and just observe the different types of distortion. Let's see here. Step 16. They're trying to have you calculate open loop gain. So basically what they're doing is they're having you do the previous step. They want you to back off the frequency and or amplitude until no distortion is present. Then you're going to look at the small signal at VN2 and comment on its changes as frequency of VS2 is increased. So let's take a look at that really quick, right? So VN2 is right here. If the circuit is performing normally, you'd expect this to be pretty close to ground, right? Just like a little small ripple. If the circuit is having a lot of distortion, this VN2, so clipping would be one type of distortion that we talked about before. So if you're railing out at a fixed voltage of 5 volts right here, the op amp is incapable of controlling that input terminal anymore through the feedback network. Therefore, VN2 is going to bounce around. So that's kind of like your clue to when you know that you've decreased the frequency and the amplitude of the signal enough. Then you can walk through the remainder of the steps to calculate, what's the magnitude of V out 2, which is just the peak to peak value. What's the peak to peak value of VN2? That's how they're calculating the open loop gain from that. So again, through 16, don't worry about 17 on. And that's it. I will wrap up talking at this point. So I'm going to jump over here to the chat forum. I'll take a look. All right, how's everyone doing tonight? Do you have any questions at this point? All right, let me ask the first question. Did everyone receive their op amps? Perfect. All right, I got some yeses. Has anyone started on the measurements part of the lab yet? Have you attempted to build it up?
Yes.
All right, nice. Is everything going okay, or have you had any major issues?
We just did we got to step 10, and we reached the issue with well, not an issue, but we saw the clipping at like 4.2 volts and negative 3.7, and we thought maybe there was something wrong with our circuit since it was so off from the 5 volts and the negative 5 volts, but apparently that was all good, so no issues.
Yeah, that's a good point. So a lot of that just has to do with your data sheet, right? And understanding like not when it comes to clipping, like not every op amp is going to get all the way to the rails. So like positive and negative 5 volts, for example. So that's one thing to be aware of. But there are some op amps out there. They're called rail-to-rail amplifiers that are capable of doing that. I'll tell you, let me come back to this real quick so we could just maybe illustrate a couple of those points. Let me go back to the wave gen. Just going to go back to a nice, simple 1 kilohertz signal. So we got 1 volt, 0 volts offset. That looks great. I'm going to come back here to the scope. Let me minimize this. I'm going to go to millisecond per period. Wow, man, they got like 1 hour per division. It's crazy. All right, here we go. So let's add a couple of measurements, right? So let's see, define measurement. We'll do channel 2 because that's all we're really concerned about for clipping. So we'll do maximum and we'll do minimum. Okay, close that out. Okay, yeah, we got those right there. All right, so let's come back, and on my wave gen, I'm going to intentionally cause it to clip. So we'll come back here. So it looks like this is a great example. So we got clipping at like 4.26 volts, negative 3.69. So one of the lab steps, I'll kind of illustrate it here, but what they're asking you to do is like figure out a DC offset on the input signal. So they're asking you to like shift this up or down to maximize the peak-to-peak output signal without getting clipping, right? So right now we got, let's start off here with our maximum and minimum. So I'm definitely capable of going higher compared to, make sure I'm reading into this right here, right? Compared to going lower. So what I mean by that is, if this is like a perfect sine wave without, well, the point of what it's clipping on the sine wave. So as this comes up, this is getting up much higher on the sine wave than it is when it comes down, right? So what we want to do, since it's capable of going higher, we want to shift it up, okay? So what's the difference between them? So we'll just call it 3.7 to say, we'll call it like 4.25. So that's like 0.55. Let's see here. So you got to keep in mind too that we have gain with that. So we got 0.55 between the two. Then I'm going to divide that by my gain of 3.1. So I really want to do like a DC offset of like 177 millivolts. So I can come back here to the wave gen. So I'll type in 0.177, hit enter, come back to the scope. I must not have hit run. Okay, here we go. There we go. Okay. So then what we're going to want to do, what it's essentially asking you to do, is to figure out what's the largest you can do on the input, right? So you can come in here, you can calculate it by looking at it. So I dialed it back a little bit. Another trick to eyeball it is just to look at the width of the clipping up here. So you can see I'm still a little off because like the width of clipping up here is wider than the width of clipping down here. So we'll still back it off just a little bit. Come back to, keep forgetting to hit enable. And almost there. Let's see here. 1.4, hit run, go back to scope. So I'm getting pretty close, right? I'm almost there. So essentially this is what it's asking you to do, is just kind of figure out like what's the ideal center point in here between the two clipping points to center up your output. Then what's the maximum input signal that you can apply before you get clipping on the output. And really what they're asking you to look for is they want the circuit to clip at the same time on the top and the bottom. So that's kind of like what you're looking for. And now granted, when you do this step, like don't spend 45 minutes going back and forth trying to perfectly fine tune it. Just observe it and get the general idea of what's happening. Let's see, any other questions? All right. Let's see. So I think what I'm going to do tonight, well, let me ask this, just to be honest, okay? So there's two different ways we can go about this. If you're going to continue working on it right now, I'll leave my computer up and running at this point. I'll just check back, frequently to see if any questions are popping up. If you just tuned in tonight to get some direction and get some input to get started, that's great. I encourage you just to go off and work on your own at this point. I will be available for office hours on Tuesday. But, honestly, over the course of this weekend, if a lot of questions pop up, it's a 3-day weekend for me. I'd be willing to even, since we're a little, we got a little sidetrack because of technical difficulties, I'd be willing to hop on this weekend at some point. If anyone needed a quick sanity check on anything, you could just shoot me an email or post a comment through Moodle. I would jump on. What I will do is when this session closes out tonight, it takes a little bit for it to convert to a postable link, but I will make sure that it gets posted either tonight or first thing this morning. Office hours on Tuesday, good question. Tell you what, let me look at my schedule real quick. Let's see, today's the 8th. Oops. Sorry about that. My calendar is a little slow right now. I'm trying to access my work email. All right, come on, connect. Here we go. Let's see. So let's see, Tuesday, October 13th. Let's see, I'm going to be in a meeting from 7:30 through probably 1 p.m. How about 1 p.m. on Tuesday? Does anyone have conflicts with that? So let me post that. 1 p.m. on Tuesday. Does that work for everyone? If not, I'm flexible. We can make it later in the day to accommodate schedules as necessary. Okay, so it sounds like 1 p.m. is good. So what I'll do is I'll send out an email for the entire class just to notify them that it'll be 1 p.m. on Tuesday. If that doesn't work for, for some, but it works for others, I'll tell you what, I'll do one at 1 p.m. Then if you can't do it because of work constraints or other classes, I'll jump on later that night and we can do another one. That's fine. I just want to make sure everybody's up to speed and you're getting the information you need to, complete the labs and stay on track. I think that's it at this point. You have all the knowledge you need and just best of luck, get to work. For some reason, like I said, if your circuit doesn't work the first time, if you're having some issues, just take a deep breath, take a step back, kind of go through that little flow that I gave to you that gives some recommendations on where to start, starting with your test equipment. I mean, I could give you a prime example right now, right? Like if I don't turn my supplies on, what does my output look like? Horrible, right? So that's a pretty good indicator. This is like troubleshooting 101. My output is flat, but my input looks great. Why am I not getting an output? Well, the first thing I might want to check is my power supplies, right? That's a problem. Turn them on. So it's little things like that. These are the kind of skills that you're going to need to develop to tackle these circuits. And thankfully, I mean, we're talking about one op amp and two resistors, but not much more. Hey, Justin. So, okay, you posted slides, but not a video for a lab outlined. No, there should be a link there. Let me go back here. So this recording link right here for October 5th, that's when I talked about this intro to op amp slides. Here. Is that what you're referring to? Yep, that's it. Okay, yeah, feel free to watch that video again. I went into more detail tonight, I rushed through what I talked about in that video, but that one is just a slower pace. Walk you through everything. Let's see. All right, any other questions?
Yeah, Professor, just a quick question. Are we going to use these, the LM741s for future labs in this class?
Yeah, so you're going to use them. Great question. Yeah, thank you for bringing that up. That was actually the last comment that I wanted to talk about. So you're going to use them for lab 3. Then you're going to use them for lab 4, which is a single supply op amp lab. So last thing I'll point out is for next week, I would like you to attempt to do steps 1 through 4. Okay, the hand calculations. I will admit, so you're only doing one configuration in this next week. Okay, we're talking ahead now. This is definitely a little bit more tricky circuit. You got some more components in here and a capacitor. If you don't get through all the hand calculations, that's fine. The first night, I anticipate what I would normally do in a lab. I'm going to give you a complete crash course on this circuit and talk about what it is, what the capacitor buys you, how having a potentiometer, which is this resistor with this arrow, which is called a wiper coming into it. So we'll address that. But to be specific to your question, we'll be using the 741 op amp for this lab. But for all future labs going forward, it will just be diodes, a MOSFET, and a BJT. So you won't be using the 741 after the next lab, lab 4.
Okay, so then my other question would be, then after we're done with that lab, do you want us to send the op amp and the capacitors back to you, or can we send it back with the pivot kit?
No, honestly, just leave them in the kit. It's fine. I'm not worried about that. If it ends up, as long as it ends up back in the school lab, that's all that matters to me. That's fine.
Okay, thank you.
No problem. Let's see. All right. Any more questions? All right. Well, get to work. Best of luck with the op amp lab. Hopefully between the previous video I posted and I will post this one as well when I get off so you can reference it as you work through the lab. I also highly encourage you to use the Moodle forum. So let's go up to the top here. So your lab discussion. If you're encountering any issues, I encourage you to take a screenshot or post them in there. Normally in a lab setting, you'd be able to walk over to the group next to you and talk to them and see what they're doing and kind of collaborate and get ideas off of each other. Unfortunately, you got to do that in a virtual setting. So don't have any fear. If you're encountering a problem, more than likely someone else is, so post it. Hopefully you get some quick feedback. I will monitor it. And if it's a growing trend where a lot of people are experiencing it, it kind of gives me a clue to jump in and figure out where everyone's getting hung up. So use that. Let's see, I think that's all I got for you. So get to work. And, if you're not going to do it tonight, that's fine. I completely agree. It's towards the end of the evening. And go ahead and work on it over the weekend if you got time. And if there's, a significant amount of people that encounter some issues over the weekend, and I'm seeing some input, via through the lab discussion, or if you're emailing me, I'll then look at the my weekend schedule, and I'll set aside some time to host an additional office hour to get together with everyone on through Zoom to address some of those problems that help keep you moving along. So, all right, that's all I got for you.
Professor, just one more question. Sorry.
Yeah.
So as I was attempting with my lab partner on the lab, it says I don't know if you went over this, I might have missed it, but it's like on step 9, to the last part of it, it says record the value of VOS obtained by other laboratory groups. Is that necessary or?
No, it's not. Yeah, thank you for bringing that up. Hey, yeah, great comment. I'm going to be honest, like these labs were drafted up years ago and I inherited them, and they're really tailored for the lab equipment and working in a live lab environment. So as we go through these, this is a great example. Don't worry about comparing it with other groups. Feel free, like if you want to post it in the discussion forum, like, hey, this is what we got for our group, that's great. Someone else can concur with what you got, but don't let that hold you up. The only thing I will say this, what I've seen in the past, okay? If you come up with a value that's like 5 millivolts, just keep moving forward, okay? If it's just slightly outside of what they're recommending here, if you have something that's like half a volt, something's not right. So go back and check your circuit. All right. Any more questions? Let's see, I will point this out. I just realized I didn't bring my laptop charger home with me, so I'm down to about 15% right now. So let me know if you want me to stay on till I'm probably gonna wait till about 8% if you need me to stay on for a little bit. I just want to make sure I stop and I save this video so I can post it. That's my key concern right now. So any more questions? All right, well, have fun, get to work. Remember, it's these labs, yeah, they got some directions, in terms of what you're trying to follow, what you need to follow and do, but feel free to tinker and play around with it too. Kind of just, see what the Tesla equipment can do in some different settings and have some fun with it. I'll be monitoring my email account, and if anything pops up and you need me to jump on over the weekend, I will host another Zoom session for you and help you guys out. If that's it, everyone have a great night, and best of luck with the lab assignment.